This is Josh Wright with JW Math Tutoring. This video is going to go over the 6 new problems that were recently added to Bluebook practice tests 1 through 3 the last week of July 2024. So let's go ahead and get started.
But life is a dream that calculus could never predict.
All right, so I'm going to go through the 6 new questions that were recently added to Bluebook practice tests 1 through 3. All of these are from Module 2B, the harder of the 2 second modules for the math section. So just keep in mind, if you have not taken Bluebook practice tests 1 through 3 in the Bluebook app yet, you will come across these questions as you take the test. So this video is basically to serve 2 purposes. First, it's for people who have already taken Bluebook practice tests 1 through 3, but are now completing these new questions, as extra practice, so to find the solutions for them. But also, the original videos I uploaded for the Bluebook practice tests, obviously have the old questions in it. So if someone does take the new versions of the practice test with these questions on it, you're not going to find it in my original videos because obviously those have the old ones in. So there's going to be a link on those to come to this video to show you the updates, solutions for these new questions. All right, so with that being said, these are all, by the way, going to be in the order of the practice test 1, chronological order. So like 8 and then 16, and then practice test 2, 6 and 17, and then practice test 3, 8 and 15. Okay. So this first question, Bluebook practice test 1, question number 8. You can see it on the screen here. It's a little tricky question to understand and read through, but once you actually figure out what it's asking for and how to do it, it's actually not that bad. So the way I would approach this is following. I would start off and I would say, okay, let x equal 0. Okay, if you plug in 0 for x into all of these equations, all of the exponents are going to go to 0, and then any number raised to the 0 power will all turn out to be 1. So all of them when x equals 0 are going to be 48. So now we're looking for the value of c that we increase x by, i.e. add to x, such that we're going to increase the y value by 27. So in other words, what do I need to make x into such that I will end up having this whole part, next to the 48 turn out to equal 27? So essentially what you do is you go through and you look at the exponents and you realize, okay, this is 3 to a power. What do I raise 3 to make 27? Well, it's 3 to the third. Therefore, the 1/2 x has to equal 3. So if you solve that, you find out that x has to equal 6. Then you look at the next one. I already have 3 to the third, so that's already 27, right here. Therefore, the exponent, it might be difficult to see, it's 1/6 x. Just that's equal 1, because I just want 27 to the first. So the exponent, which is 1/6 x, just has to equal 1. So again, x has to equal 6. This is actually going to be the same for all of them, as you'll find out. Now for the next one, 9, which is really 3 squared. So this one is a little tricky because it's 3 squared, and then you also have it to the 1/4 x. So when you raise exponents, you multiply them. So really what this turns into is 3 to the 2/4 x, 2x over 4, 2/4 times x, which is really the same as 3 to the 1/2 x. So this one is actually identical to the first one in that, it's the same equation. You set that equal to 3 because you want 3 cubed for 27. So x is going to equal 6. The last one, again, here you have 27 already. So if you just multiply these together, we have 27, we have 1/3 x times 1/2, so we have 1/6 x. Again, that equals 1. This one is actually identical to b. Therefore, again, x is going to equal 6. So when you increase x by 6, the number you get as your output, your y value is going to increase by a factor, excuse me, of 27. Because if you plug in 6 for all of these, you'll see you get 48 times 27. Okay, you can just verify that in Desmos, verify that on a calculator. So now what this question is really asking is, which of these equations has 1 over c, in this case the c is the 6 that I just found, as its exponent, or excuse me, as its coefficient on the exponent. So the correct answer is, of course, going to be letter B, because in A, the coefficient is 1/2, in C it is 1/4, in D it is 1/3. Those are all wrong, but in B it is 1/6. So letter B is the correct answer to this one. Now, you could do some stuff with this in Desmos, like you can graph some of these out, and you can use it to help you figure out what the C value is. But I don't see, as of right now, I don't see a short, easy way to figure out that C has to be the value of 6. Next up, this is question 16 on practice test 1, module 2B. So one thing to know about this question, this is actually from the linear non-adaptive paper test number 1, module 1, question number 26. So again, this is linear test 1, module 1, question number 26. So this is actually not a brand new question. They just took one question from the paper test that was unique and they threw it into practice test 1. So just be aware of that. If you've already done the linear test 1 unique non-overlapping questions, then you've already done this problem. You can probably skip this. All right. So the quickest, easiest way to solve this is just in Desmos. So that's pretty much the only solution I'm going to show because I think it's just so much quicker and so much easier than some of the other methods. First thing to be aware of, these two lines are the same, okay? The second one is a multiple, everything's multiplied by 5. So this system of equations is really infinite solutions, meaning it's really one and the same, it's one line, just written two different ways. If you don't realize that, if you type them in Desmos, you'll see they just overlap each other. So we only need to do one of them. We only need to type one of them in. So if I graph the top one, now, all we need to do is run through the answer choices as points, and we're going to put in a slider, and we're going to see which of our answer choices are on this line. So let me just zoom out. Okay, see, there's the point way up there. It says in the problem for each real number r. So regardless of what r is, it has to be on the line in order to be the correct answer. This is not on the line, nowhere near the line, so this is wrong. So now we can move on to answer choice B. Okay, so if you look at this one, notice no matter where I slide it, it is on the line. So B is going to be the correct answer. Now, you could try C, you could try D. They're not going to be on the line. I won't spend time typing them in, but just, you can go and verify it for yourself. But this is going to be the correct answer. Now, just for an alternate explanation, not from just to show you, the other way to do this is to pick a value for r for each of these expressions and plug it in and then work it out to a point and then take that x and y value, plug it into one of the equations and see if it works, if it's on that line. And you could just work that out manually, or you could, again, go to Desmos, type in the equation, then just type the point value in, and you could visually see if it's on the line. So for example, for A, I let r equal, let's see here, 5. The reason I did that is because that gets rid of these fractions, and it comes out to a nice point value of 8, 34. Because it basically becomes 1 plus 7 is 8, and negative 1 plus 35 is 34. All right, and that is not going to be in the lines, if you plug that in. For B, I just let r equal 1, and the reason is because even though you see fractions here, since you're adding them, just keeping the numbers on top is fine because what ends up happening is you get -3 plus 7, which is 4, and then the 4 divided by 2 just reduces to 2. So you just get the nice point 2 comma 1. For C, I let r equal 1 again, and you get a nice point of 1 comma 3. For D, I let r equal 1 again, and you get a nice point of 1 comma 2. Notice D is just the opposite of B. They just switch the x and y coordinates. So you can go through again, plug these in, whether top or bottom line. I just use the top because the numbers are smaller. The only one that's going to work is B. 2 times 2 is 4, plus 3 times 1 is 3, equals 7. 4 plus 3 equals 7, so it checks, it confirms. Next up, we have the 2 questions from practice test 2, again, module 2B. The first one is number 6. So first I will show the kind of the traditional way, how you could do this by hand, then I'll show you how you could do this in Desmos. So if you're going to do this one by hand, you're going to complete the square and put this equation into standard form. Then we're going to get an expression for p on the right side where the equal to r squared, and then we'll just set that equal to the np and get the value of n. So first thing I would do is I would divide everything on both sides by 8 just to make the numbers much smaller and easier to work with. You do that, you're going to get x squared plus 14px, and I'm going to leave a blank, which I'll talk about a little bit, plus y squared minus 8py, and again a blank. And on the right side, it turns into negative 56p squared. All right, so now we complete the square. We take 14p, take half of that, and then square it. But the 14 divided by 2 just becomes 7. 7p squared is 49p squared. Do the same thing for the y terms. Divide the b value by 2 and then square it. So half of negative 8 is negative 4. Negative 4 squared, 16p squared. And of course, we have to remember to add those 2 terms on the right side. So the left side, technically, I'm not going to bother spending time putting it in standard form because we don't need that. All we care about is the radius. So on the test, if you don't need the center of the circle, we don't need to actually factor it and do all that. So on the right side, you add up negative 56 plus 49 plus 16. You should get 9p squared. And again, standard form equation of a circle, the right side is equal to r squared. So that means the radius is equal to the square root of 9p squared, which is just 3p. And they tell us in the problem that the length of the radius is equal to np. So therefore, n just has to equal 3. So the correct answer for this one is 3. Now, let's see how you could do this in Desmos. So let me go ahead, just move this over here. Okay, so I'm going to type in the entire equation, and basically what I'm going to do is add a slider. And then we're going to move that slider, and you'll see that the value of the radius is irrelevant. So let's see here. What do we... 848p squared. Why is it not giving me a circle here? Oh, it's because I put an extra x in there. All right, there we go. Fixed. All right, so here is our circle. I let p equal 1, right? So now if I click on my circle, okay, I have 2 endpoints of my diameter. So notice the total distance from the top one to the bottom one is, well, 7 minus 1, or 6. So therefore, the radius has to be equal to 3, because 6 is the diameter. Just divide that by 2. Okay. So now they tell us also the length of the radius, which I just said is 3, is equal to n times p. So it's n times, what did I let p equal? I let p equal 1. So 3 is equal to n. That's the answer. Look how much quicker and faster that is than all this work that I wrote out. All right, but you're saying, okay, what about if I choose a different value? Let's say, I don't know, I just expanded over here whatever, 3.6. So these are decimal values, like whatever, it's annoying, but I'm just gonna show that hopefully I should get the same thing. So notice again, I have two diameter endpoints here. So to find the total distance across, I just subtract the two y values. So I've got 25.2 minus 3.6. 21.6. Now, that is equal to the diameter. Sorry, 21.6. So I got to divide that by 2 to get my radius. So I'll just cut that in half. 10.8. Okay, so my radius is 10.8. Let me just jump over here. And again, from the problem, I know my radius is equal to n times p. Well, 10.8 is equal to n times 3.6. So my n value has to be whatever 10.8 divided by 3.6 is. So let's just do that. I get 3, same answer. Doesn't matter what value p you choose, n's always going to be 3. So that's how you could do this problem entirely in Desmos. You do not need to put it into standard form. You do not need to do any algebraic manipulation of this question. All right, next question up is, again, practice test 2, module 2b. It is question number 17. So on this problem, you are given the equation of a line. Again, it's got a constant, random letter in here. And this is a function, and it wants to know about, though, the x-intercept of the graph of this function shifted up 9 units. All right, so a couple different ways you could do this. The algebraic way would be to do the following. First of all, if this is the function to shift it up 9 units, you just add a plus 9 here. So at the end, this becomes plus 26. Then you're going to distribute this out. So in other words, you're going to get 120 dx plus 126 d. Okay, and then you have the plus 26. And it's asking about the x-intercepts. Hopefully remember, for x-intercepts of a graph occur when the y value, y coordinate is equal to 0. So this is just set equal to 0. So now what you do is you go ahead and you solve this for x. So you subtract over 26. You subtract over 126d. So we get negative 126d minus 26 on the left, 120 dx on the right, divide by 120d, 120d. Technically, you could simplify these. They have common factors of 2 or whatever, but you don't need to do any of that. So the correct answer for this is just going to be basically letter A. All right. Now, here's how you could, though, solve this problem in Desmos. Okay, so what we're going to do is we're going to go to Desmos. I'm going to type in the original function with the d. And then remember, the original function has the plus 17. All right, so now I'm going to add a slider for d. I'll just leave it as that. And then I'm going to do a new function, and this new function is going to be the original with the plus 9, because that's what we're finding the x-intercept of. So first of all, take off the original. We don't need that anymore. All right, the x-intercept of this function is negative 1.267. So I just run through my answer choices, and some of these are going to be a pain to type, but that's fine. And we're going to see which one matches the x-intercept value. So right off the bat, notice negative 1.267, negative 1.266666, eventually 7. So this just confirms that A is the correct answer. I mean, you could go through the others and you could type them in and, whatever, and plug them in, but none of them are going to match. So this just confirms correct answer is A. Again, graph the function, add a slider for D, then graph the translation of the function up 9 units, then go through the answer choices, typing in the expressions and seeing which one gives you the same value for the x-intercept that you get from clicking on the graph. All right, now we are up to practice test number 3. This is, again, Module 2B. This is question number 8. And this one, there are actually like 3 different ways that you could solve this problem. The first 2 ways I'm going to show are using similar triangles. Third way is going to actually involve using basic trig. It's actually much longer because it's got many more steps, but the individual steps themselves are not that difficult. So if you label the picture, you got 121 over 3. You've got 11 root 130 over 3. We want to know DC. So method 1, or we could call approach 1. If you know your geometric mean theorems, basically I'm going to use those in solving this. So basically this right here, this line segment, this leg of the overall large triangle, is the geometric mean between the entire hypotenuse of the large triangle and this part of it. So what that means is if you set up a proportion, it's like 11 root 130 over 3 over 121 over 3 is equal to AC, the entire hypotenuse, over 11 root 130 over 3. Basically, the side that is the geometric mean is what gets multiplied by itself, is what gets squared. So essentially, you do cross multiplying, you get this, and you get this. So when you do that, okay, what we end up with here is 11 times 11, 121. Root 130 times root 130, 130. I'm not going to multiply them together yet. 3 times 3 on the bottom, 9. Okay, on the other side, 121 over 3 times AC. So what do we do next? Well, the 121s will cancel out. You can multiply by 3 over here, and then that 3 will cancel out with that. So that's gone. So AC is now solved. Basically, this whole thing is 130 over 3. Then to find DC, just this little part over here, all you have to do is take the whole hypotenuse, 130 over 3, minus AD. This is AC, this is AD. Same denominator already. Keep the denominator at 3. 130 minus 121 is 9. 9 over 3, that just reduces to 3 over 1, or 3. Therefore, DC is equal to 3, and that's going to be the correct answer. So again, that is method 1. Method 2 is going to be similar to this. It's going to use a geometric mean theorem, but it's also going to use Pythagorean theorem as well. So let me just erase some of this work here. And I'll show you how to do it this way. And then again, method 3 is just going to use basic trig. Okay, so first thing I would do, again, this is method number 2. I would find BD using the Pythagorean theorem. And I would do this all in Desmos, which I'll bring up in a second. So basically it's like 121 over 3 squared plus BD squared equals 11 root 130 over 3 squared. If you go ahead and rearrange this, you're going to get 11 root 130 over 3 squared minus 121 over 3 squared. Okay, and then you would square root. This is originally BD squared, but you square root both sides, to solve it. So let's go to Desmos. Let's find out what BD is equal to. So first thing is I need a giant square root. Then underneath it, I need 11 and another square root, 130. Divide that by 3. It's going to... There we go. Now, need another parentheses. Okay, good so far. Okay, so there I have the whole expression typed in. Okay, square root of 11 root 130 over 3 squared minus 120 over 3 squared. Okay, we get 11. That means BD is a nice, integer value of 11. Now you can use another geometric mean theorem, which basically says that BD, the 11, is the geometric mean, okay, between the two parts of the hypotenuse it splits up. So one part is going to be the 121 over 3 AD, and the other part's going to be the DC that we're looking for. So now you cross multiply, and you get 121 equals 121 dc over 3. The 121s cancel out. You have a 1 left here, and then you just multiply by 3. dc equals 3. Same exact answer, little different approach, but still using the idea of a geometric mean. Okay, here is solution number 3. Actually, see if I can just get rid of all this. Okay. So this is again an alternate solution. So first thing I would do is I would find the measure of angle A, because I know that the cosine of A is equal to the adjacent side over the hypotenuse, 121 over 3 over 11 root 130 over 3. If you do that for A, just on your calculator, you're going to get something like 15.255. All right. Then you could find the measure of angle C. Okay. Measure of angle C is just going to be 90 minus that. So it's going to come out to, so 90 minus A, basically, because they're two acute angles, that have to add up to 90 in a right triangle. It's going to come out to approximately 74 point, what do I have here? 44. Okay. So now we know this angle, 74.44. We knew this one, 15 point, I think I rounded off to 15.26. Now, in order to get DC, there's technically two different ways you could approach this. You could do the following. You could kind of take from method 1, you could say cosine of, or no, sorry, it's going to be, sorry. You could say sine of C, 74.44. I'm looking at the large triangle as a whole thing, is equal to the opposite, 11 root 130 over 3, divided by the hypotenuse. And this would give me the whole value for AC. And so AC is going to be 11 root 130 over 3 divided by sine 74.44. So if you punch that in to a calculator, okay, so we have that, and now divided by sine of 74.44. Let me just make sure I am in degrees mode. Okay. So that's what you get for AC, and then you would have to subtract that minus, you'd have to take that value and subtract from it 121 over 3, to get what's left for DC. So if I go back to the calculator here and I do this and I do minus 121 over 3, it comes out to 3.06. Now here's the problem. Like the 74.44 is not exact. It's rounded off. So ideally you would do this on a graphing calculator where it could just carry the full decimal down, and it would come out exactly to 3 for its value. But that's one way you could do it. The second way is you could get BD using the Pythagorean theorem, which we know is 11, and then you could do basically tangent of 74.44 equals opposite 11 over adjacent DC. So DC is equal to 11 divided by tan of 74.44. Again, if you do this out, basically, if you carry the full decimal out on a graphing calculator, you're going to get the exact value of 3. But like when I do it right now, it's not going to be, see again, it's going to be like 3.06, it's rounded. So because it's a free response, you don't know exactly, like, is it exactly 3? Is it 3.06? Whatever. Whatever. So if you're going to do this approach, I would strongly recommend you do it on a graphing calculator where you can copy the full decimal down from step to step. But those are 3 different ways that you can approach this problem. Number 8, practice test 3, module 2B. All right, last question we have here is number 15. Again, practice test 3, module 2B. So in this question, basically, it's actually not that bad, even though it looks quite complicated, because you can use the sum of solutions shortcut, negative b over a, to look at these two equations and determine what their sum of solutions is. So for the middle one, the b value is 0. There's no x term here. So the sum of the solutions to the middle one is just 0. Now, you could also figure that out because basically, even if you graphed it in Desmos or if you factor it, it's like x plus 3, x minus 3. So the two solutions are just opposites. So when you add them, they just cancel. Okay? Same thing for the last one. It doesn't matter what p is, that's irrelevant. We know that the sum of the two solutions is going to be the opposite of negative 16 over 2. 16 over 2 is just 8, so we know that this is 8. The first parenthesis, the first factor, has one solution to it. It's basically going to be, you set it equal to 0, it's 3x equals negative p, x equals negative p over 3. So you just add all those up and you set it equal to 20 thirds. So you could do this by hand. You could just go straight to Desmos and do this. But however you want to do it, the answer for this one is going to come out such that p is going to equal 4. Because it's basically, first I would multiply everything by 3 just to clear the fractions, say if you were doing this by hand. So it's negative p plus 24 equals 20. Negative p equals negative 24. Therefore, it's p equals, sorry, you subtract 24. P equals, here, let me just go down here. Negative p equals negative 4. Therefore, p equals positive 4. Again, there are some parts of this you could get in Desmos. Like, you could graph these and you could get the two solutions, and then you'd still have to add them to get that they equal 0. This one, you could graph it and you could put it in a slider. Technically, it's not going to change the value of the solutions. Okay, so whatever you choose for p, if you still add the two x-intercepts up, it's always going to equal 8. And then the first one, though, you do have to know that it's just going to be an expression, negative p over 3. But once you get these values, which again, you can get this one and this one, you can get from Desmos if you need to. Once you get that, you just add them all up, set it equal to 20 over 3, and then solve that equation for p. And again, just to review, you could just type that equation into Desmos, use an x instead of a p, and it'll give you a vertical line at 4. All right, so I hope you enjoyed this video. Again, I went through the 6 new questions that were added to Bluebook practice tests 1 through 3 very recently, basically just sometime July 23rd through July 25th. Don't know exactly when. Check out my other video, which has more information about when the questions were added. Also, check out my other digital SAT math videos. I have one about a basically 3 to 4 month study plan that I use to help a student increase the SAT math score by over 200 points. I also have a video, basically like a backgrounder or a primer, which goes over everything you need to know before you start studying for the digital SAT math section, talking about the Bluebook tests and a little bit about Desmos, and also talking about the linear tests and the question bank and the skills insight tool and all kinds of good stuff and free resources out there. Otherwise, if you like this video, please do give it a thumbs up. Subscribe to my channel and sign up for notifications, or leave any comments that you have below.